So let's introduce Thevenin's theorem now. Thevenin's theorem is really important, and outside of KVL and KCL, you're probably going to see Thevenin used a whole lot in engineering. It actually permits the reduction of a complex network to a much simpler form so that you can analyze the circuit that you're working with. So what do I mean to do? What I mean by that is you can analyze networks with sources that are not in series and parallel, kind of like mesh or nodal analysis, but Thevenin's theorem kind of focuses on one portion of your circuit. You can reduce the number of components required to establish the same characteristics at the output terminals. Well, I'll show you what I mean by that. You can investigate the effect of changing a particular component on the behavior of the network without having to analyze the entire network after every change. In your labs for mesh and nodal analysis, we changed a resistor in there, and you had to go back and do mesh and nodal analysis a couple of times, and it can be kind of difficult to do when you change all of your equations. With Thevenin's theorem, however, we can take the portion of the circuit that you're not going to change and reduce that down to just a voltage source and a resistor, and that makes that analysis much easier if you want to continually change that load resistor, as we did in the lab. So essentially what we're saying is that any two-terminal network can be replaced by an equivalent circuit that consists of just a voltage source and a resistor. And as shown here, this is our E Thevenin and our R Thevenin. They actually have their own names, our voltage source and our series resistance. So basically what we're saying is we can take this portion of our circuit right here and reduce it down to something that looks like this, and that makes our circuit analysis at this point in the circuit much, much easier. So what's the procedure for this? Well, the first thing we want to do is to take away that portion of the circuit where we're looking for the Thevenin equivalent circuit. And we're just going to take it away temporarily and mark those terminals A and B so that we know where to put the Thevenin equivalent circuit back at the end. The second thing we're going to do is look for R Thevenin. And to do that, we're going to set all of our sources to 0 and look for the total resistance between A and B at that point. And the third step is to find E Thevenin, which is where we put our sources back, and we calculate our open circuit voltage between the points A and B. So I'm going to work through this problem just so you kind of see what it is that we're doing. This is a pretty simple circuit in and of itself, but we're going to reduce it down even further using Thevenin's theorem. Thevenin's theorem says that we can reduce any two-terminal network down to simply a voltage source in series with a resistance. Okay, so what we're going for is something like this. And where this would be E Thevenin and R Thevenin. So the procedure that we're looking at with Thevenin's theorem is to find that E Thevenin and R Thevenin for our circuit. So in this example shown here, what we're going to do is remove the portion of the network where the equivalent circuit is to be found. So basically we're analyzing, for some reason, maybe we want to analyze what happens when we change the load, when we increase it or we decrease it. Well, to do that, we would pull off that portion of the network, and then we would reduce this other portion that's left. We would reduce that down to our Thevenin equivalent circuit right there. So the process involved is, first of all, remove this RL, which we have done in this circuit. And then we're going, and of course, mark the terminals. We do that so that we know where to put this back. So I'm going to put A and B, right? So we'll put A and B back at the end. So the first thing we're going to do is calculate R Thevenin. And we do that by setting all the sources to 0. So of course you remember that that means that your voltage sources are going to be shorts and your current sources are going to be opens. And then we find the resistance between the terminals. So essentially we're taking this 9-volt source right here, We're going to short it out down here, and then we're going to insert an ohmmeter right here and measure from A to B. Now it's really important to keep in mind that we have to measure that resistance at those terminals because that makes a difference in what our Thevenin resistance is. If for some reason we put that ohmmeter here, we would get a completely different resistance. So you have to be very careful that you know where you're putting your ohmmeter. So we're actually measuring between A and B here, and notice when we do, what we see is that R1 and R2 are connected over here, and they're also connected over here, which connects up to our meter as well. So R1 and R2 are actually in parallel with each other to calculate our Thevenin. So our Thevenin would be 1/1/3 plus 1/6, which would be 2 ohms. Now, once we have found this, then step 3 is done, and I want you to actually ignore the fact that we did step 3. Put our Thevenin to the side. I'm going to write it way up here. I know that our Thevenin is 3 ohms. I'm sorry, 2 ohms. Okay, our Thevenin is 2 ohms. Leave it alone. Okay, it does not matter anymore that our Thevenin is 2. We'll come back to it at the very end of the work that we're doing here, because the next step is to find E Thevenin. And E Thevenin is a different process from finding R Thevenin. So once we have done step 3, then we write down what we learned and we move on. We do not use this anymore. We throw that circuit out and start again. Now E Thevenin, we put our sources back, all of them, and then we're looking for the open circuit voltage between the terminals. Basically, we're putting a voltmeter here at A and B. Okay, so the red lead would be at A, black lead would be at B, and we're measuring the voltage there. Now in this case, that red lead is connected to right here, and the black lead is connected to right here. So we're essentially measuring the voltage, that's going to be E Thevenin, which is essentially the voltage across the 6 ohm resistor. So how do we calculate that? Well, this portion of the circuit is open. Okay, I know it looks like it's connected because they've drawn in that E Thevenin there, but it's open. So basically we've got a series circuit here where our I sub S is just 9 volts divided by 3 plus 6 ohms, or 9 ohms. And we've got 1 amp of current there. So 1 amp of current means that I've got 3 volts drop across my R1, and my drop across that 6 volts is of course 6 volts. 6 ohm resistor is 6 volts. So E Thevenin in this case is just the 6 volts. So I'm going to go back up here. I found that E Thevenin is 6 volts. So that means, let me see if it's drawn here. Yeah. So that means when I draw this back, I've got my E Thevenin, which is 6 volts, my R Thevenin, which is the series resistance for that particular source, is 2 ohms, and then I put whatever portion of the circuit I removed in the beginning, I put it right back between A and B. So what we're saying is this circuit right here that's all in blue, I just replaced with a single voltage source and a single resistor. Now what that means is whatever voltage and current I had at terminals A and B before, I still have at terminals A and B with a simpler circuit. And the reason this is so important is because now I can change RL many times, and the circuit analysis on that is very easy because it's a simple series circuit now, and I don't have to do quite as much work with analyzing the circuit.